All right, electricity. What do we got here?
Um, electrons doing stuff.
Need more.
Okay. I wrote the flow of electrons through a conductor.
This is totally true. I'd probably add something like um, to do work. All right, so what's voltage measure?
Force of electrons.
And an amperage?
Flow rate.
Volume, not in terms of like the three-dimensional thing you measure, but the number of electrons that pass a point. All right, AC, DC?
AC is alternating current, and DC is direct current.
So the electrons only go in one direction for direct current, and an alternating current, they switch back and forth at a very, very high rate. Where do we use AC?
In our in our in our homes.
Okay.
Electric motors, laundry,
Car.
power transmission.
All right, so I can't really say that.
Well, there are DC motors,
Yeah.
but generally they just aren't as good.
Yeah, I can't say that either because the Tesla car, those DC motors are pretty good.
Wait, really? I thought those were alternating current magnetic motors.
Why would you think that?
I read somewhere that I thought they were, but it might have been one of the old ones, or it might have just been wrong.
So they're taking the DC from the battery and turning it into AC?
It takes an inverter. That's what I thought. But
And you lose power during the inversion process. I squared R losses. Yeah, it's a
dang.
brushless DC, or yeah, it's a brushless DC motor.
Okay.
Homes, lights. I mean, I used to be able to just straight up say stuff like motors and lights, and but you can't really say that anymore because there's so much stuff that's DC. How about I
Well,
can?
you can't even really say transmission anymore because there are specific instances where they do use high voltage DC.
Where are they transmitting high voltage DC that's not a lightning bolt?
Here let me pull up an article. It's from a specific power generation facility.
Well, the transmission lines that are over your house, those are absolutely AC. Like laundry, dishwasher, most lights, uh, you know, hot water heater. DC electronics. Anything with a battery. All right, write a single replacement reaction identifying substance reduced, substance oxidized, reducing agent, oxidizing agent. All right, so let's do
Lithium.
and.
NaCl.
Really? Okay,
It's
that's
a
fine. So
What,
this,
is it too lazy?
no, not at all. Not lazy at all. Just not a big voltage differential, so this probably wouldn't be something that somebody would actually do. So
Okay,
we've got this guy's oxidized. This guy is reduced. This is well. So that makes you the. So what makes lithium the reducing agent? Nothing?
I wrote the opposite. I wrote that lithium was the oxidizing agent and NaCl was the reducing agent.
That's incorrect because the lithium itself, it has an electron and it gives the electron away. So that makes it the reducing agent because it gave its electron to the sodium, thereby taking the sodium's charge from +1 to 0. So it reduced sodium's charge.
Okay.
And then if I think about that from the opposite direction, the sodium is a +1 charge, and what it's doing is it's taking the electron away from the lithium ion, and doing that causes the lithium ion's charge to go up. So that lithium ion was oxidized. So the sodium ion in the NaCl is the oxidizing agent.
Okay.
What's more rustable, aluminum or magnesium, and how do you know?
I said magnesium because it's higher on the activity series.
Yeah, that's it. So it's if you're looking at the activity series, magnesium is here and aluminum is down here. So that makes you more active. So being more active means more likely to give up electrons. Acids have the ability to do what to some metals, but not all metals? What is it that they can do?
Acids can oxidize metals, or some metals.
Back off. Which metals?
I put down sodium, or not sodium, but hmm.
So any metal that's above hydrogen on the activity series is rustable. It will be oxidized by an acid, which is most of the metals, right? What was below hydrogen on the activity series? Does anybody remember?
There was royal metals, right? Like gold and
Noble metals. I guess you could call them
Copper.
royal metals. That's fine. So copper, gold. What else?
silver.
Silver.
Would
One-
iron be one of them?
No.
No, not iron.
the easy way to think about it is the stuff that's valuable, the stuff that you think of that is that jewelry is made of and that coins are made of. Although don't think about nickel when you think about that, because that's not actually elemental nickel. That's a nickel that's an alloy.
Yeah.
Write a chemical reaction to justify your response. Okay, so HCl plus. You guys did this last quarter. The zinc's charge is 0 here, and over here it's +2. The hydrogen's charge is +1 over here, and over here it's 0. So the I don't know why I put a circle around that. Oh, it's just 0. So your charge goes up, so you're oxidized, and your charge goes down, so you're reduced. Okay. Draw out this galvanic cell. All right, great. So KNO3. We'll do.
Does it have to be that specific salt, or can it be any salt?
What does it need to be? Anybody?
A salt that conducts. That is conductive, I mean.
Okay, that's part of it. What does that mean? A salt that conducts?
It has to be soluble.
Has to be soluble. If it's soluble, and you need to be a little bit more specific than just soluble. You wouldn't want to pick something like picking table salt would be fine until one of the metals that you're using has the ability to precipitate out with that. So I wouldn't use NaCl if I'm doing silver as one of my if silver was one of the metals, because then I'd make silver chloride and I would lose charge to the silver chloride salt, which the battery wouldn't be able to break apart. I mean, if it was a big enough battery you could, but a regular battery, no. So which direction are the electrons going here? Or sorry, let me rephrase this. Let's do this. I'll just put tin here, and magnesium here, and magnesium ion here, and tin ion here. With I don't know, it doesn't really matter. I'll just put nitrates. Which direction are the electrons can flow?
From tin to magnesium?
Is that right?
Is tin the anode?
You're telling me.
Okay. Well, my guess is that tin is the anode and magnesium is the cathode, and so they're traveling to the right.
Just because that's how I had it oriented in the last picture?
Yes.
That'd be incorrect.
It's magnesium.
So look on the list and you'll see magnesium is higher on the list than tin. So
Okay.
specifically what's going to happen?
Magnesium is more active than tin,
Yeah.
and so will it steal the electrons from tin?
No. It's the exact opposite. But I want more specifics. We know we're going to have electron flow this direction, but be more specific about it.
The magnesium is going to dissolve
The magnesium is going to send electrons where?
into the tin.
No.
Into the ionic solution.
To here. That's where the electrons end up. This tin can't accept electrons. It's a metal. Its charge is 0. It can't become negative. So the only thing that can accept it is this tin ion. So the magnesium solid sends electrons to the tin ion. And in this case, it'd be 2 electrons.
So it goes through the wire, through the metal.
Yeah, so the magnesium bar, one of the atoms of magnesium turns into magnesium +2, and then it sends 2 electrons, wire, 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 through this bar, and then this tin here, ion, says, hey, look, there's 2 electrons right there, and I'm positively charged. I will attach myself to that.
So then what's the salt bridge for?
What did I just send this direction?
The magnesium ion.
No. I sent 2 electrons.
Okay.
So this got -2 bigger. Okay? I need to take a potassium. I need to put 2 potassiums in here. Because what does putting 2 potassiums in do?
Equalizer.
Balance out the charge. And so if this side over here loses 2 electrons, it became +2 bigger. So then I have to take 2 nitrates that are each -1, and they go in and neutralize the +2 that side became.
So, this is a battery, so where, like, how do you get the energy out of that?
Where this voltmeter is, you would put something here. A light bulb, a calculator, a car, something. The load is going to be in a wire in between the cathode and the anode.
And it's not the electricity isn't coming from the actual electrons coming from them passing through that point, right?
Say that again?
I'm trying to kind of conceptualize electricity. So the electrons are passing through the wire, and in that middle point, something is being like powered.
Some work is being done there. That work could be heat, that work could be lights, that work could be mechanical.
So are those electrons are they just passing through that point and going directly to the other side, or are they going through
Maybe. Yeah.
Okay.
They're going to go through something that you want. So in your phone, it will pass through electronics. It will pass through the display on its way to the cathode side.
Okay.
So we had a little discussion about somebody asking you to grab something on your way to go do something else.
Yeah.
So you're going to pass by there anyway, and your end goal is to go out and come back where you came from, and somebody just has you do something along the way. And that's a key point about electricity, that the electrons always end up where they started. So when the electrons leave the Dow's dam, they have to go back to the Dow's dam. They
So
make
is it
a
going in
circuit.
circle then? Is
Sure.
it going through the wire? And
I would call it a circuit and not a circle, because it's certainly not going to be circular, but
Yeah.
it ends up where it comes. So how do you stop the electricity's flow? You break the connection anywhere. Anywhere where the connection is, the electricity stops. You usually stop it at like an outlet on the wall, or you pull the plug, and that's how it gets stopped. But if somebody runs into the power pole out of your house and breaks the pole and the wires come down and they break, then you've broken the connection. So the electrons can't get to your house and they can't get back to where they were before. So even if the wire that's sending electrons to your house is intact, if the wire that's leaving your house to go back to where the electrons came from is broken, it stops. All flow stops.
I was wanting through the diagram on the homework. I wasn't sure, how you would figure out what's in the ionic solution.
For our purposes, whatever metal you're using, it'll be an ion of that metal, and then the anion that you're going to use, just anything soluble. Which is why I always throw down nitrate, because I know it doesn't make a solid. There's no precipitate that's going to form with a nitrate. So you could throw down acetates, just something that you know is soluble. So that second rule, or maybe it's the third rule, nitrates, acetates, chlorates, and perchlorates. If you use any of those anions, then you don't have to worry about a precipitate forming.
Okay. And then how did you choose the K? Was it just because it's whatever, it just makes a salt?
Yep. I chose nitrate because it's a nitrate, and I chose K because it's one letter.
Okay.
I mean, I could have put Li, or potassium is used frequently, sodium is used frequently. Doesn't really matter. It was literally me being lazy and picking one letter. And then we want to draw the shorthand notation for this. So the way this starts is it's a magnesium that's a solid, and that thing turns into a magnesium That's a +2 charge. That's aqueous, separated by a salt bridge. And then I have tin. That's a +2 charge. Turn into tin. That's a solid.
And then that collects on the tin.
In this case, it's going to collect on the tin bar. Yep. Questions about that?
Just to clarify, magnesium is the anode, right?
Yeah. The anode is where the electrons come from. So the anode is going to be the thing that gives up its electrons, so the thing that's higher on the activity series. Is there anything else that this could be used for besides just a battery?
You said like a calculator, but I mean, is that not what you're going for?
No, I don't like I don't mean as a power source. Could this be used for something other than a power source?
To collect some tin metal?
Okay. Maybe I wanted to collect some tin metal somewhere specific. Maybe instead of this, I switch it up and I have. This is going to be a poor drawing, but that's par for the course.
I don't
Yeah.
know what that is, Jim.
We're going to talk about it right now. Probably, I don't know, it doesn't really matter. This can be zinc solid. And there's a sort of E in there. Yeah. So you got a Harley Davidson motorcycle with a very large straight pipe on it, and it's super shiny. How did it get super shiny? Because the pipe itself is made out of iron or steel. What's happening here?
The exhaust is getting coated in a very thin layer of chromium.
Yep. So zinc is higher on the activity series than chromium is. So this zinc bar right here is constantly sending electrons over to this because it's connected straight to it. So I've got this piece of metal that's inside this this container. They usually close this up, stuff something in here like a cork or something like that so the interior doesn't get coated. But now I've got electrons on the outside of this steel container, and these chromiums that are +3 attach themselves to that spot. And this steel pipe gets totally coated in chromium. So why would somebody do that?
To make it look nicer.
Okay, so it's shiny. Great. Anything else?
It protects it.
It protects it from oxidation. The chrome does a better job of not rusting than the steel would under those high temperatures. So if you want to take any piece of metal and make it look different, so like they call it gold filled, which I don't know why they call it gold filled. It should be gold covered. So they'll take a piece of copper, a ring or something like that, and they'll stick it into this vat, and they'll put gold ions in the vat with it. And so the gold ions attach themselves to the copper. And you've got a copper ring that's coated in gold. So why would you want to do that?
It's cheaper.
There's no other reason. It's cheaper. So neither one of them is going to oxidize that much, but the gold is definitely more expensive. So it'll look like gold and it'll act like gold for a while, except it's a really, really thin layer of gold. So you put that on your finger, and what's going to happen?
Your finger doesn't it isn't that what gives you the like green ring sometimes around your finger?
Yeah, but why do you have a green ring around your finger?
Because the gold oxidizes?
No,
Because the gold
The- your skin acts like sandpaper and literally rubs it away from the inside of the ring. So now I've got this ring and there's no gold in the middle here. And now I've got that copper on your skin. Well, your skin is dead, but it still has a bunch of oils and acids, and you like touch tomatoes and oranges and all kinds of things, and you end up oxidizing the copper just because of the constant moisture and constant oxidizing agents that your hand is going to have on it. And when that happens, the copper turns into copper oxide, copper 2 oxide. And copper 2 oxide is green. And it's also a rust, and that rust isn't very structurally sound, so it just rubs off on your skin. And so that layer of dead skin underneath the ring gets basically stained with copper. So copper oxide.
This is kind of a weird question, but do we know why it's green? Like why it has that color?
Yes, but you're also asking like why is the definition of you're asking why the definition of a word is what it is. That's its nature. So what it comes down to is when we were talking about, you guys remember
The fires, whenever we like lit the fire and it's a different color based on what we used.
Yeah, we didn't do that though.
The mixing of orbitals.
The molecular orbitals. Do you guys remember this? And we had an unpaired share of electrons in that position, and that caused us to have oxygen be magnetic. Well, when light comes down and hits these things, certain wavelengths are absorbed and other wavelengths are not absorbed. So the color is based off of the orientation of the electrons. In this case, it would be copper 2 oxide. And so when light comes in and runs into it, some of it gets absorbed and some of it gets reflected, and the combination of what gets reflected is green. And that goes for every color that you see. So if you look over Fatima's shoulder, there's some really nice blue back there. And if you look at Madeline's sweatshirt, it's maroon. And where did Ronaldo go? He had lots of colors on his shirt. And each one of those dyes is doing that. They're either they're reflecting and absorbing particular colors to give you that color. All right, so let's go back over to the notes. Where were we?
Question.
Yeah.
Is magnetron using a magnetron to coat glass and stuff similar to electroplating with the electric, or completely different?
You cut out there right when you asked your question.
Oh, is using a magnetron to coat things that aren't normally conductive like glass and stuff similar, or is it completely different?
It's very, very similar.
Okay.
So we talked about the battery. Solving.
Sorry.
All right.
Yeah, sometimes I get really big single time hiccups.
Okay.
She died.
I didn't die. My soul just left my body for a split second.
What?
I said my soul left my body for a split second. Mom! I love you.
She just put it back.
Oh my god.
This is not supposed to be here. This is from last year, and I can't get rid of it. All right, whatever. That's fine. Okay, so that battery that we had for the homework, it was magnesium and it was tin. So we haven't discussed how we calculate the voltage created by batteries, but this is how you do it. So Does anybody notice anything different about this activity series than the one we had a couple of pages, 5, 6 pages up?
It,
Besides the fact that there are numbers there?
I don't see helium.
You mean hydrogen?
Yeah, I see hydrogen. I
You-
thought it was helium. I don't know why.
You thought it was the least reactive substance in the entire universe on an activity series?
It's one letter off. Okay.
Just one letter, no big deal. Just, you know, the difference between being very reactive and the most common element in the entire universe and the least reactive substance to ever exist.
Okay. It's like instead of just one like ion or one metal, it's a bunch. Or yeah. Well, it looks like reactions.
There were reactions.
Yeah.
It's backwards.
Oh.
The other has an element that turns into an ion, and this one has ions that are turned into elements. You okay with that? It doesn't matter which direction that it's written, but whichever kind of table that you get, either an oxidation table or a reduction table, every single substance in the table is going to be written in the same direction. So even if the substance doesn't want to do what's listed, everything on the table is listed in going one direction. Either all the atoms are losing their electrons or all the atoms are gaining their electrons. Everybody's being oxidized or everybody's being reduced. Okay?
But what about the bottom where it has the elemental fluorine?
What's happening to the elemental fluorine?
I see. It's gaining electrons.
Every single time what I've got happening here is something is gaining electrons. Somebody rang the doorbell and it doesn't sound like anybody's answering it, so 1 second.
It's time to revolt, people.
No.
Hey, stop. That's weird. You like unmuted and muted yourself rapidly.
No, that's just my computer being stupid.
Oh, okay. I thought you did that on purpose.
It said, Viva la revolution.
Viva la revolution.
Viva la ravioli.
Viva la ravioli.
Viva la spaghetti.
Viva la revolution. Oh,
Viva la química.
it's almost break time anyways. It's 3:08. We usually break at like 3:20, I think. Or like 3:30.
Before 20 be a better break time.
4:20. 4:20 is end class time.
I know, it's great time for a break.
Oh my god. I need coffee, but I don't have creamer. Oh, my parents went shopping and I didn't have some creamer. It's stupid.
Drink
Me
it
too.
black.
No, I hate black coffee. It tastes bitter and ugly.
Well, you know what they say.
No, Gage, I don't. What do they say, Gage? I want
Once
to
you
hear it.
go black, you never go back.
It was just a bored 3-year-old. Okay.
Amazing. Was it your daughter?
No, just a random 3-year-old walking down the road, down Highway 35 by themselves and like ringing door. Yes, it was my daughter.
I don't know where you live, Kobe. You got like
Doesn't matter. How often has a 3-year-old walked up to your house and rang your doorbell?
I live in a suburban neighborhood, okay?
You didn't answer the question.
It happened in Texas. It's called a ding dong ditch. Have you ever seen that?
By 3-year-olds?
Yes, by three.
Lies. Not 3-year-old dogs. Okay, so every substance on this table is being written in a way where they're gaining electrons. And so when we do an oxidation and reduction reaction, one of these is going to be written backwards because it has to be. Because everybody's written gaining electrons, and in a redox reaction, something's gaining the electrons, but something else is also giving the electrons away. So we have to look at what the voltage is and flop the sign accordingly, depending on which element is gaining, which element is losing electrons. So in our homework, what was the magnesium doing?
Magnesium was giving electrons to the lithium.
Is that happening here?
Well, in this one, they're both gaining electrons.
Okay, so is it happening here? Is the magnesium giving its electrons away?
Yes, because it's higher.
That's not what I asked. I'm asking in this table, does this table show magnesium giving electrons away?
No.
It shows it gaining electrons, right? So while the number 2.38 is correct, the sign is incorrect because that's not what the magnesium was doing in our example battery.
Yeah. Okay.
So in our sample battery, what voltage do we assign the magnesium?
Positive 2.3.
Positive 2.38. So there's the tin written down there, circled. Is that what the tin was doing?
Yes.
The tin was gaining electrons. So however this is written, that's correct. So the tin doesn't really want to gain the electrons, but it's sort of like, nah, I don't really want that. Okay, I'll take it. Because the voltage that it says, it's only negative 0.14 volts. So it's not really against the idea. It would prefer not to, but it's not hard. Where the magnesium is like, I don't want that thing. I have 2.38 volts of no, I don't want it. And I'll give you 2.38 volts if you take these 2 electrons away from me. And the tin's like, all right, I guess I'll take those, even though I don't really want them, but you want to get rid of them so bad that I'm willing to accept those. So on the right, I have the magnesium written where the sign is flipped because that's what happened in our example. And I have the tin written as is because that's what was happening in our example. And so this battery will end up generating, that's wrong. That math's wrong, right?
Yes.
There's a mystery one there.
Should be 2 point. I'm pretty sure.
Maybe I can.
You can turn it into, yeah. That's a Z. Amazing work.
There we go. So this battery generates 2.24 volts. Is that good?
Yeah, yes, that's a charger, right? A phone charger?
No, phone charger is 5,
Okay, so half a phone charger. So no.
but still yes.
What's a good amount of volts?
Well, we're going to talk about that in a second. I just want to make sure that everybody understands what's going on with this, where in any given redox reaction, so let's say, what situation would need to occur if I wanted to have calciums and, say, cadmiums create a battery? What would I need?
Volt-wise?
No. Like what substances would I need to have in my battery to have cadmium and calcium creating a battery together?
Like the ionic substance? Or the
I
ionic
need calcium solid.
Yeah.
And I need
cadmium.
cadmium ion. Are we okay with that?
I thought you needed both solid electrodes.
Didn't last time. We didn't when we talked about the electroplating of the Harley Davidson pipe. Okay, so let's look at it like this. Let's say I had cadmium and calcium, both solid metals. So calcium's higher on the activity series, right? So it would give electrons to cadmium. But does cadmium need any electrons?
No.
It's an element in its elemental state. Its oxidation state is 0. So grab your periodic table that you obviously have on your desk because, you know. And
Yeah.
cadmium's element number 48, second row, the D, last column. What's its oxidation state? Two. So all the cadmiums in the universe have the ability to have an oxidation state of 0, which means its protons and electrons are equal to each other, or +2, where the proton number is 2 bigger than the electron number. That's it.
I thought it was I thought it was 0 plus 2 and minus 2. Better.
Then didn't I just say +2?
Yeah, but also minus 2.
Hell no. It's a metal.
Okay.
Metals
Oh,
can't be
okay.
negatively charged. So your options are the metal has all of its possible electrons to make it an element, or it can lose some electrons. And how many electrons can cadmium lose? 2. And that's it. It either has everybody or it's missing 2 electrons. All right? So in this example here where we've got calcium metal and cadmium metal, can the calcium give any electrons to the cadmium metal? This is like a fundamental thought.
Can the calcium give electrons to cadmium metal? No,
You're correct. Why is the answer no?
because it's a cadmium. It's a metal.
Its charge is 0, right? What would happen to it if it had gained 2 electrons from the calcium?
Would
Well-
it just disperse? Like not take it?
Well, what would its charge be if it actually could do that?
-2.
Not a possibility. So
Yeah.
is this a battery? Cadmium metal and calcium metal? No.
But isn't that why we have the ionic solutions?
Well, I didn't give you that option. There's no ionic solution here.
Okay.
So this cannot form a battery.
So in the previous example, then would it be calcium solid in like an ionic solution with cadmium in it?
Sure.
Okay.
Can this form a battery?
Yes,
How come?
because it's positively charged, and so it wants to be balanced, so it doesn't have a charge.
So I want you to think about metals with an oxidation state of 0 having the ability to give electrons away because they can. What can that calcium metal not do?
It can't take electrons.
It can't take electrons. Period. So let's talk about the cadmium below it, the one I have written right there. What can that cadmium do?
It can take electrons.
It can take electrons. What can it not do?
It can't give more electrons away.
It can't give any more electrons because cadmium, I picked it specifically, it's got 2 oxidation states, 0 and +2. It cannot give any more electrons, and it could gain how many electrons? 2 and only 2. It can gain no more than 2. It can gain no less than 2. It has to gain 2 electrons. All right, so what about this situation? What's going to happen here?
Nothing.
Nothing. Nobody has any electrons to give anybody. So even though the calcium is more than willing to give electrons to the cadmium, it's already given its electrons away. So it can't actually do anything. What about this situation?
So the cadmium is at a 0, and the calcium is at a +2 charge. So
So
the cadmium could give electrons to calcium.
So the cadmium could give electrons because it has electrons. Stop talking. You, stop talking. No. Hey, stop. Okay, I'll go. Just go. I'll follow you.
Oh man. Oh gosh. I just feel like it's time to go drop my mug off in the kitchen.
No, it's not that.
I know. It's such a mess. I've gotten too accustomed to break time. Not today.
So the calcium can't give electrons. It could accept electrons. The cadmium can't accept electrons, but it could give electrons. So what's going to happen here?
They will trade.
Nothing is going to happen here.
Oh.
Why? Because calcium's higher on the activity series. So even though the calcium could accept the electrons and the cadmium could give the electrons, it won't happen. So there's
because cadmium is less reactive.
because cadmium's less reactive. That's it.
Can I ask a question then?
Yep.
Real quick.
Yeah.
All of this is talking about DC, if correct.
Yes. There's no AC is not generated in batteries. It's not possible to generate it with a battery. The only way to generate AC is by using an alternating current generator.
Okay.
So there's only what we have are the metal is an element or the metal is an ion. Those are our only options. And for metals to create a battery, the metal higher on the list needs to be a metal, and the metal lower on the list needs to be an ion. That's the only instance where a battery will occur.
Are we
So-
going to do anything using hydrogen?
Sure.
There's a
So you could make cadmium give the electrons to calcium, but what would you need to do?
You need to force it with
So-
adding power to the system.
So what do we call that? What's the generic term that we call it?
Is that whenever the
Super easy word we all know. You do it every night, probably. Charging. That's it. So if you made a calcium cadmium battery, this would be the point where the calcium has exhausted itself. It's given all the calciums have given all their electrons to the cadmium, and all the calcium is an ion, and all the cadmiums are solid. Great. And now the battery's dead, so you plug it back in, and that electricity is used to knock the electrons off the cadmium and give them back to the calcium. And then you end up with calcium solid and cadmium with a +2 charge that's aqueous. And then, so this is night, well, probably at night. And then during the course of the day, you have the battery discharging. Does that make sense? So it's not cadmium and calcium for you guys. It's going to be an organic cathode and lithium as your anode, because that's what we're doing. Although the reaction itself isn't super simple. It's actually quite complicated. But the end result is lithium is giving electrons to something for your lithium-ion batteries. So can you see why lithium is a especially good choice for a battery?
is this at the very top of the activity series?
Giving us the highest voltage all by itself. So these are called half reactions. Why are they half reactions?
Because they don't have something else reacting with it, it's just electrons.
Okay. Anything else? They can't happen by themselves. That lithium reaction cannot happen. That electron, so in this case, the electron that's being given or forced back onto the lithium, where did it come from?
Another element.
I have to have that other half reaction. So a whole reaction is whichever one of these and some other element. So these don't exist in a vacuum. I can't get, say, like a lithium to accept an electron unless I have a substance that's willing to give the electron to the lithium. So the reason that they're written as half reactions is we have the ability to choose, whichever combinations of rows that we want. So if I want to make a battery out of lithium and potassium, it would be stupid, but it's possible. Why would it be stupid?
Tiny voltage difference.
Look at the voltage differential between the two. Point
Oh, there.
what is it? 0.12? 0.12 volts. That's a bad voltage if you don't know that. What would be a great battery? If we could have a lithium fluoride battery. right? What would be, look at the voltage differential. 5.91, that's
Yeah.
monstrous. A single battery cell generating almost 6 volts would be terrific.
That would be positive 3.04 minus 2.8.
Plus.
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 But the fluorine down there is a plus already. Oh, right.
One of them is written correctly and one of them is written incorrectly.
Got it.
Why are we not rolling around with lithium fluoride batteries?
Is it too powerful?
Nobody has a way to make them, engineer them to be stable at this point.
Where did we get all the numbers?
Research.
Faraday and Nernst are almost exclusively the people who came up with these numbers, and they've been around for 125 years. Do you notice anything in particular about the numbers, just in general?
They go from negative to positive.
Okay, great.
kind of in a
Negative to
order.
positive, anything else? There's a 0.
Yeah.
Hydrogen is the standard by which all the other voltages are measured from.
Oh, that makes sense. Hydrogen is almost always the standard.
No, carbon's usually the standard.
It is? Oh, yeah. I don't know why.
But since carbon isn't on this list, they picked hydrogen because it's an acid and it's the odd man out, not being a metal. Okay, so these are the way that the voltages were calculated is they created those voltaic cells or galvanic cells with so let's say they did a lithium aluminum one, and then they got a voltage out of that, and then they did a lithium zinc one, and they got a voltage out of that, and then they did some subtraction. So you can figure out the voltage that the lithium is generating based off of the difference between the zinc and the aluminum. So you just do a bunch of those reactions and keep pairing things up differently, and then you can just do a little tiny bit of algebra to figure out what each individual half reaction's voltage is. Or you can just have the metal react with hydrogen. And whatever voltage is generated is the voltage by the metal because hydrogen's the standard at 0. We okay with that? So there are lots of different battery combinations. Can you give me a reason why one battery combination is chosen over another? There's lots of different reasons, but somebody got one for me?
Higher voltage differential?
Yeah, you create a higher voltage in that one reaction. Okay, so it produces a high enough voltage. What else we got?
How expensive materials are.
Really important is how expensive are the materials. So the more abundant a particular metal is, and the easier it is to refine, the more likelihood that metal is going to be used as a battery source. What else we got?
How stable the reaction would be?
The stability of the reaction is why lithium wasn't a battery right out of the gate. I mean, we've known for over 120 years that lithium has got the highest half voltage, but we can't use it specifically because if it touches water, it explodes. So they had to come up with an electrolyte that allowed the reaction to occur. Remember what I said the electrolyte is like?
Gasoline.
Yeah, it's a hydrocarbon. It's a non-polar substance that has embedded electrolytes in it. So it's got to be something that is not water, so it doesn't explode and or create hydrogen gas when it touches it. But it itself can't touch oxygen because the moment it does, it's going to be hot enough to catch on fire. So there's a lot of engineering issues with this, and then a lot of cost issues, and a lot of just, is there enough of that stuff around? Or are we using that stuff for something else? Like iron isn't typically used for batteries because it's used for a lot of other things.
Quick question on lead acid battery.
Sure.
The lead acid uses lead and hydrogen, right?
It uses, it's kind of funny, it uses lead and lead. It uses lead and lead-4 oxide. So the lead itself goes from being 0 to being +4 and back, and they use sulfate, specifically sulfuric acid. The sulfate and sulfuric acid as the electrolyte to drive that reaction. And it's used in a car because lead's inexpensive, sulfuric acid is inexpensive, it's not explosive, it's filled with water and a little bit of acid, and it lasts a long time. Like, when was the last time you changed your car battery? How long do you expect your car battery to last before having to change it?
A couple years.
A couple? If it doesn't last at least 5 years, that battery was garbage.
Or you have red shorts, which kill batteries.
Yeah, but that usually only happens if it gets overheated or is in a car accident, or you buy a really, really, really cheap battery. So just can you guys tell me what voltage you create with a calcium cadmium battery?
Like negative or 2 point 2.36.
That sounds good. 2.36. So the calcium is the thing that's going to be giving its electrons away. So I find calcium on the table. I see that it's written backwards. So I take the 2.76, negative 2.76, and flop the sign to make it 2.76. And then I find cadmium on the table. And this is what cadmium would be doing, which would be cadmium ion accepting 2 electrons, turning into cadmium metal. And you have to force those electrons back on the cadmium. So it takes 0.4 volts of electricity to make that happen. So I lose some of the calcium is trying to give those electrons away, and I lose some of that because some of that energy is used to shove the electrons back onto the nickel, the cadmium. And so we end up at, what'd you say, 2.26? 2.36. 2.36.
36?
Also a pretty good battery, charge-wise.
Okay.
Is there any other reason why you would or would not want to use a particular battery? Or a particular metal in a battery? I
You
feel like,
don't want it to overcharge or overpower something?
no.
Like the weight of a material, like the density.
Sure, I mean, lithium is a great choice because of the density, and lead's a bad choice because of its density. What do people typically do with batteries? What do you do with dead batteries? Yourself.
Oh, throw them away.
Throw them away. So do you want to fill that thing with something like chromium that turns into something that's toxic to people? No. So chromium isn't a good choice because the people who make batteries know what people are going to do with batteries. So why are people not concerned about car batteries being made out of lead?
Because cars are heavy and so it doesn't really matter.
No, I'm talking about the environmental toxic effects.
They charge core charges.
Yeah, if you want a new battery, so if the battery is $100, they charge you right off the bat $125 or $150. How do you get the $50 or $25 back? You bring the old battery in. Or you walk into the store with the dead battery and give that to the cashier, and then they give you the other battery just for the $100. So they just simply make it worth your while to take the dead battery back into the store, which is what Oregon has been doing for, 40 years, right? 40 plus years. You buy a pop can, it costs you a nickel to take that with you, and you get that nickel back if you bring the can back. And now it's a dime. That was kind of a big deal when that switched from a nickel to a dime. Year before last, I think it was.
Yeah.
All of a sudden, people who have these stockpiles of pop cans in their garage because they're too lazy to return them are like, it's worth twice as much. And then the line was out the door. Out the door. And then they said something funny in the media like, all those old pop cans will only be worth a nickel if you don't return them by this time. What was the problem with that statement? There was no way to say how old that can was.
Wouldn't it say it on the can?
It doesn't matter. The reader only reads the UPC code. And the UPC code doesn't have the made by date on it. It just has a number. The
Mine
UPC
says-
code on Coca-Cola 12-ounce cans has been the same for I don't know how many decades.
Mine says HR 5 cents or OR 10 cents, so that's Hawaii 5 cents and OR 10 cents. Is HR Hawaii?
Did you say HI?
Yeah, HI.
Okay. All right. So no problem with figuring out those voltages, right?
Mhm.
The battery that we had up here, the first one we had, this copper and silver one, that's a really stupid battery, right? Silver's expensive, copper's expensive, silver's heavy, copper's heavy. They're both hard to get. The battery would be expensive, it would be heavy, and what kind of voltage does it generate? 0.46 volts. So
Nothing.
horrible
Put
battery.
it on the voltmeter on the diagram.
I had it on the voltmeter on the diagram. I did.
Pretty sure.
No.
So then is more than 2 volts a good battery?
All right, so we're gonna have that discussion right now. So the batteries that you buy and install in things like flashlights and remote controls, the quadruple A, triple A, double A, C, and D cell batteries, those batteries are 1.5 volts. Most electronic devices require 5 volts of electricity to function. They've actually for quite some time now, they figured out a way to make that happen at 3 volts. So what is it that the electronic device is trying to do with the electricity?
Dissipate it while doing work.
Well, what work is it trying to do?
Depends on the electronics. It's either producing light, producing heat, changing the state of something.
Since the language of electronics is binary, the electricity is being used to tell a transistor to say 1 or 0. That's what it's being used for. How do I get this transistor to switch from 1 to 0? Well, old transistors and many transistors is I apply 5 volts positive or I apply 5 volts negative, and I can get this thing to switch. Well, what if I'm at 4.8 volts? It doesn't switch.
How do
So
you get a negative voltage?
Change the polarity.
you just swap the sign, you just make the battery go backwards.
Oh, okay.
So if you pull apart your TA89 calculator, how many batteries are in there?
4.
4 AAA batteries.
It's got a 5th little reserve battery.
True, for your memory. Little 32 maybe, something like that, coin battery. So actually they're AA batteries, and the batteries, that calculator requires 5 volts of electricity to function. So how much electricity is 4 true AA batteries going to give you?
Goes right there.
You have 2 options, depending on how the batteries are connected. So the one on the bottom is actually how the batteries in your calculator are connected, and you know that because every other battery is flipped over. The engineering is different than what they show here. You don't align them all the same direction and they have wires. They have you actually flip them upside down, right? And then they make a connection from here to the bottom, from the top of this battery to the bottom of the next battery, and from the top of this battery to the bottom of that battery. So why are we flipping the batteries over each time? Well, this battery right here is good for 1.5 volts. So, I don't want to do this. So when I need a thicker pad. Let's do, I don't know, say red, big one. There we go. So the electricity goes through here. When it goes through this battery, how much voltage does it pick up?
1.5 volts.
1.5 volts. And then it goes to the next battery, and how much voltage does it pick up?
Another 1.5.
Another 1.5. So after it exits this battery, its pressure is 3 volts. Now its pressure is 4.5 volts. Now its pressure is 6 volts. And 6 volts is enough to run the electronics in your calculator. And 6 volts is also not enough electricity to break the electronics in your calculator. Okay?
How would the arrangement be on the top one? Would it
So
be
on the
like a
top
straight
one,
wire?
all of the positives are connected to the same wire and the negatives are all connected to the same wire. And this thing generates 1.5 volts, period. The whole battery, this whole assembly will generate 1.5 volts. Well, why is the other one generating 6 volts?
Is it just because it's one whole wire?
Yes. And the other one is, the circuit is called parallel. So the advantage of the one on top is basically, instead of just having one battery to discharge, you're going to discharge 4 batteries. So the top will provide only 1.5 volts, but it'll provide it for a very long time. So this is something like they have LEDs that will pop on at 1.5 volts, or regular incandescent light bulbs can be run at 1.5 volts. This arrangement would allow that thing to be on for a long time, 4 times longer than if there was just one battery. But the one on the bottom, since it's in series, I get a higher voltage, so I can run some other device that requires a higher voltage. Does that make sense? So, can't think of a good analogy other than like Iditarod, the dogs pulling sleds. If you had one string of dogs in front of you, each one of those dogs is providing power. And then if you had a second string of dogs with you, you have double the power, but you don't have double the speed.
Okay.
Because the dog next to it has to be running at the same speed as the dog next to it, right? So the more lines of dogs that you add, the more force that those dogs can exert on the yeah. But if I had, instead of having 4 lines of 10 dogs, I had 1 line of 40 dogs, I could make the sled go faster. Because the front dog would run as fast as it possibly could, and the second dog would be following it as fast as it could.
What if you had like 40 dogs and 2 lines?
I don't know. It's just an analogy.
So I forgot my question. I don't know what happened.
So what we get with this is the ability to make a battery at a lower voltage last a long time, or I can take the same battery and put them together and make it a higher voltage and last less time. So there are 2 12-volt batteries in my truck. How are those batteries connected?
The parallel arrangement?
Yeah, why are they connected in a parallel arrangement?
Because it needs to last a long time.
No, actually no.
Because you only need 12 volts.
Because you could not only need, if you had 24-volt battery inside of a car, you would burn stuff. Stuff would catch on fire or melt. So all of the electronic devices in your car run off of 12 volts or less, which is why you can touch anything in your car and not be shocked by it. Your car cannot shock you. It's not possible.
I guess I've been shocked by the metal, but not the electronics.
Like a static electricity thing?
Yeah.
The wires, you can literally just grab the wires in the same way you can just put your hand on the battery. It can't hurt you. I feel like we had this discussion, but I don't know for sure.
We did. You could grab the wire, but if you like put a metal ring.
36 volts is the minimum voltage to cause cardiac arrest. So if the thing that you're messing with is under 36 volts, you cannot possibly stop your heart. But this 36 number was accomplished with a person who was sick. I'm not joking. I mean, they have like the flu or a bad cold, and they're soaked in seawater. How in the hell could I possibly know this?
There's a specific instance that you're thinking of.
Because they do stuff like this. Why? Because a sick sailor in a boat that's having electrical problems and the water that he's in is being electrocuted, you want to know exactly what voltage is going to kill the kid. So they did these experiments,
So they,
put a sick person in water, and then ran electricity through it to see what voltage would stop his heart. Yes, that's been done.
yeah.
But it was in a secure environment. So as soon as his heart did stop, they pulled him out of the water and, hit him, got it going again. Said thanks.
Was it voluntary?
Who knows?
I mean, you were in the Navy.
Yeah, but these experiments were done before stuff like
Yeah.
this would cause an outcry.
Before ethics.
Well, not just before ethics, but think about a time where a person would be willing to do this.
Whenever, yeah,
World War II.
yeah. All I'm thinking of.
I
is
can't go on the boat. I can't go because I've got, I don't know, flat
Yeah.
feet. I can't be drafted. I can't go to war. I want to go fight the Nazis and I can't. So how can I help? Electrocute me in a boat while I'm sick. That kind of stuff happens. And it just drives me crazy knowing stuff like that. And then you have people saying, you can't make me wear a mask, Costco.
Yeah, right. Like we don't fear anything anymore.
Well, it's not even that. It's like they're acting like
I'm sure.
Like they're fighting people when we're in a war with a virus and you're helping the virus, so you're actually fighting for the other side. So you should be put in jail like Asian people were put in jail during World War II. That's my opinion. You're walking around Costco with no mask, you get arrested and you get put in a, what do they call it? An internment camp. Yeah. Okay, so
We should go on break so I can deposit my mug.
okay, I'll see you in 5 minutes.
5 minutes, you got it. Good. I'm scared. I have received a banana. Banana time.
All right, that's been 5 minutes. Mm, mm. There's just a little story here about Napoleon Bonaparte when we noticed how to make batteries, when we figured it out. The different countries of the world were trying to fight over who had the most powerful battery, sort of like most powerful armies kind of stuff. And when Napoleon had heard about this, he thought it was dumb and thought that he was much more powerful than the battery. So he went to the Sorbonne, which was the most prestigious university in France at that time, and he just walked in and grabbed their most powerful battery. And at that time, it was several hundred volts. So this would be like you just taking like screwdrivers and shoving them into the wall outlet for your dryer. Not a regular wall outlet, but your dryer. And then getting hit with that electricity. I guess he never showed back up at the lab after he was knocked unconscious. But it didn't kill him, sadly.
It would have killed him if it was AC.
And you said that was Napoleon?
Yeah.
Oh man.
If he hadn't awoke and had died, then I wouldn't had to have read War and Peace. Because it never would have happened.
It's a good book.
It was like every other Russian book ever written. Terribly depressing.
Amazing.
Okay, so one of the batteries you guys are most often familiar with is that lead acid battery or car battery. So why are the cables marked red and black when you're trying to jumpstart somebody's car?
So you can tell the difference between ground and I don't know the other one. I know that one's ground and the other's something else.
The positive terminal and the negative terminal?
Isn't black the ground?
Doesn't matter. What matters is that the black clamp is on either the positive or the negative, but it's on the same one on the other battery.
Oh, yeah.
I mean, it's just a wire, right?
To
So
jumpstart a car?
yeah, if the black wire is on your negative, then it's got to be on the negative on the other car. And if your red is on the positive, then it's got to be on the positive on the other car. Does anybody know what happens if you flop them?
Nothing?
Really bad things for the car getting jumped. Not good things. Usually, I mean, nowadays there's a fuse that they have near the battery, so it will recognize that and pop before the car explodes. It's electronics. but the thing that was happening most often was the fuel injection system, which is electronically driven, would be fried. And those were like $1,000 just for the part. So problem. The reason these are so big is the number. So what you're trying to do is take a several hundred to many several hundreds pound motor and get the internals moving. After the car is started, the battery doesn't do anything but provide a circuit. The electricity from the battery doesn't actually power anything. The alternator on the car powers the radio and the headlights and all the rest of the electronics in the car. So the only purpose for the battery is to make this whole motor turn over. How did we used to do this? How did we used to get the motor to turn over before batteries? You'd hand crank the thing, right? There'd be a huge spring. You'd pull the crank out and then you'd release the spring and the spring would cause the motor to start turning. And once it turned, then the combustion could start and then the motor would run itself. And there wasn't any electricity in the car then. It didn't matter. It was just the motor was running. So,
back there, the older ones didn't even have a spring. It was just a 1-to-1 to the crankshaft.
oh, I guess if the motor is small enough, that's totally possible. I could see that with our tractor motor.
It doesn't even have to be that small because I have it's a inline 6 white. I think it was a 2-ton or 1.5-ton truck. It was an inline 6, and you could still compression start it because the way it was built.
Yeah, but compression starting is not the same thing because when you have it in first gear and you're going to pop the clutch, the way that the gearing works is that motor is spinning at a couple of hundred times a second. And you're not going to be a minute, not a second. And you're not going to be spinning the motor a couple of hundred times a minute with a hand crank. That's just, you're not going to get there.
Well,
go
you
ahead.
actually ran it slightly rich, and then you did that first explosion was what did it.
Sure. Okay. I mean, that's basically how you start every lawnmower and, right, super rich and give it a good pull. So, what this is doing is just providing the mechanical force, the electrical force to turn into mechanical energy to turn the motor over. But this is at 12 volts, which is a very low voltage. So the reason it's 12 volts is we don't want fires in cars. Fires in cars don't get along. Cars go into accidents. I don't want that car to catch on fire because of the battery. If the car is caught on fire, it's got nothing to do with the battery. It's because there was some kind of metal on metal spark happening. So if I'm only at this 12 volts and voltage is the amount of force that the electrons are providing, so I've got a bunch of like baby electrons, right? A bunch of 5-year-olds trying to push a car. So how do you get 5-year-olds to push a car up a hill? You get a lot of them, right? You get a lot of them. So the amperage on these is, I mean, probably the lowest is say 350 amps, but mine's at like 1200 for the two batteries combined. So it needs a lot of these electrons that have very little pushing power to get the motor to turn over. So those are your options. You could have a really high voltage battery that doesn't have very many electrons and goes dead if it doesn't start in the first time. Or you could have a smaller battery that produces a bunch of less powerful electrons that eventually get the car to turn over. I mean, one of these, if you use this to power if you use the correct inverter, this thing would power your cell phone for weeks. But then you're lugging around a 50-pound battery.
Why do cars get to the point where you have to keep turning it and it's like not turning on? Turning the key, I mean.
Take it to somebody to do maintenance.
I know, but is it the battery that is doing that, or
is the motor turning over?
So you turn the key and you get that like startup sound, but it doesn't like nothing actually starts.
If you get that startup sound and the motor is turning over, it's not the battery because the battery is doing its job. The only job for the battery is to get the motor to turn over. So if it's turning over and not starting, you probably have a problem with either your timing or your ignition system, or possibly fuel system, or maybe you're out of gas.
Just one of my old friends had a super old Jeep. Not super old, but like an old Jeep, and we just like had to keep turning it and just wouldn't work. I'm thinking it's ignition.
Yeah, that sounds like timing to me if it's an old Jeep. This is what the battery looks like. So the we should have it up here. It's just a second. Can't remember if it's on here, but I'm not seeing it. There's only one lead. All right, so what's happening in this battery is I have lead anode, and I have a lead cathode that's covered with lead oxide, and the lead element is giving electrons to the lead oxide, turning the lead oxide's lead-4 into lead, going that direction. So it works really well. It works for a very long time, but again, it's heavy, a little unwieldy, and the voltage that the cell generates is somewhere around a little more than 2 volts total. And so to get it up to 12 volts, if you were to disassemble a battery, it would look like this, except there would be 6 cells there. So each one of those cells is in series with the other cells. So 2 volts, 2 volts, 2 volts, 2 volts gets you up to your little over 12 volts. Like if you have a brand new battery, it's probably measuring somewhere just under 14 volts total.
Are those little squares? Are those the cells that you're talking about?
No, this whole huge rectangle here,
Yeah.
is the
Cell.
is the cell. So I don't know why they're only showing 4 here. They should be showing 6. I should find another diagram.
What are the little on the anode and the cathode right above it?
The whole thing, or wait, on the anode and cathode, this part right here,
Yeah.
that's just where your battery terminal connection is to the cathode and the anode.
Okay. Hmm.
If you break open your phone or look at the motherboard on a computer, there's a lot of shininess going on down there. Some of the parts actually are coated in gold. Does anybody know why?
Protection?
You don't want any of that stuff to oxidize. And why would your computer or your cell phone be susceptible to oxidation?
Because it's exposed to the air.
No. You don't realize it, but your CPU, the central processing unit in your phone and in your computer, can be 150 degrees Celsius. It can be at super high temperatures. So people who want high performing computers, they'll do lots of different things to make that temperature lower.
Yeah, like big fans and stuff.
Giant fans. There's 8 fans on my computer, and the cooling for it is actually liquid. So instead of just being air blown over the top of it, there's a fluid that goes by like a radiator in your car.
Isn't fluid not supposed to really be in computers?
It's not touching anything. It's inside the tubes, just like the
Oh.
fluid that's inside of your car isn't touching anything. It's just in between parts.
That fluid can also be touching the components if it's non-conductive, because I've seen oil submerge computers.
Ah.
But how do you run the fans if the computer's submerged in oil?
It actually has like
Like an impeller?
circulates the fluid, and then the fluid goes into a radiator, which exhausts the heat, and then it feeds back in.
Yeah, but how does it move?
Positive displacement pumps.
Oh.
Uses mineral oil. It's pretty cool.
Yeah, but positive displacement pump seems like a poor choice. I think I would want to use an impeller, like a water pump.
Okay.
I'm sure it looks pretty cool. Oh, it does look pretty cool. This one looks like an aquarium. Oh my god.
That's usually what people do.
That's really cool. Wow. This one has a little purse in it. It's all like blue lighted too. Oh, that one has a skull in it. Oh my god, I want a skull.
That's pretty ridiculous.
Yeah, look at that. It's cool looking though.
They're absurd in the best way, and totally unnecessary for the components most people put in.
This
Wow.
this is mineral oil in here, right? They just
Yeah.
make it look like an aquarium?
Yeah.
Okay. So
Yes, I
there are
found
no
an
goldfish in
aquarium.
here,
I found
sadly,
an aquarium
because that would be
that's sold-
amazing.
Yeah.
I mean, if you could find a non-conductive fluid that could contain
Support.
oxygen, that was biocompatible.
And was aqueous to oxygen. Okay. All right. So Statue of Liberty. That's her. Why does she look like
There
that?
she is. Because time, she's been oxidized
Why is she green? We had this discussion already.
because she was made of carbon.
She's made of copper. So France made all of the panels. They gave it to us. So they what?
Did they?
They built it in France and then brought it over on boats and they assembled it on the island.
Oh,
So it gets its color because the exterior is copper, and it's in the middle of a sea harbor, so it's rusting all the time. And thought I had another picture here, but I guess not. So let's do. This is a good picture. Open it in a new tab. So what's going on here? Has anybody seen this kind of repair before? Sometimes they'll have it on old buildings.
No.
They had it on campus at OSU when I was there when they were trying to save one of the first buildings built. This is called scaffolding, but it's structural scaffolding. So what they do is they build the scaffolding and then basically they sort of pressure push pipes to it. So it's hard to see, but this is touching the exterior of the statue all the way up to the top. Then they go in and they pull the guts out. So this is made with an iron structure. This is going to be horrible, but whatever.
We can try our best.
There you go. So the structure underneath is basically just pig iron. Very heavy iron bars. And so to the exterior, they just slap on these panels. And then they also, put a staircase up in the middle of it. If you haven't been up there. You guys did know that, right?
What?
These
So
are
there's-
windows
you
right
can-
here.
You can go up there, yeah.
Yeah.
Is it only a staircase?
Yes, there's no. Are you asking if there's an elevator? There's no elevator. Yeah, sorry. Stairs. So you
Those little red lions. Oh.
what?
Oh, I just noticed little tiny red lines in the windows.
I just put those there.
Yeah.
Okay, so around the outside they put the copper panels. Well, over the course of 100 years, the copper that was on the outside was forming a reaction with the iron on the inside. So I'm copper ion because I know that because this thing down here is green, and I am in contact with iron solid. So why is this bad?
Because it'll react.
Because it'll turn it back into copper solid, and then it'll turn into iron +3. So what am I doing? What's happening here? The thing that's holding the entire statue up is rusting. Because the outside is rusting, and then the outside loses its electrons, and then the inside says, hey, copper, you want some electrons? Take mine. Well, that's not great because the copper can't hold itself up. It's too soft. If you pull that interior out of the Statue of Liberty, she would just sort of like slowly melt. Like something made out of wax put next to a fireplace, it would literally just be a puddle of copper at some point. A long time away, but it would take a while, but it would happen. So it needs to be held up by the iron because it's more structurally sound. So this was happening, and when this happened, they finally decided that too much oxidation had occurred, so they built the structural scaffolding around the exterior of it. Then they went in and they pulled out all that pig iron and they installed new steel. And then they also put huge washers, like huge giant washers that are made out of rubber in between the connections for the iron and the copper itself. And then, moreover, to be a little bit more thorough with this, there's a now there's a connection to the iron on the steel on the inside. There's just literally a wire going off to a building, and inside the building there are giant zinc bars. What are the zinc bars for?
Support?
No, the zinc bars are. This is just a wire. So there is a wire connected to a bunch of zinc bars in a building near the statue. So this copper atom right here at the very top of the spike on her crown, whatever. Let's say it loses 2 electrons and becomes it becomes +2 charge. The iron that's in the inside says, hey, you want these 2 electrons? Great. And so now I've got an iron that's a +2 charge. We'll say probably a +3 charge. And then this zinc says, hey, iron, did you just lose some electrons? Here, take mine. And now I've got zinc with a +2 charge here. So why is this a good system?
Because then the iron won't rust.
Yeah, and we don't care about the zinc.
No.
So does anybody know the term for this? What job the zinc is performing?
Replacing iron?
Yeah, there's a name for its job. So the element zinc is sacrificing itself, right? It's going from being an atom of zinc and it's giving its 2 electrons to the iron. So we call this a sacrificial anode. It's an anode because it's the thing that's giving electrons and it's sacrificing its electrons for some other object. So sacrificial anodes are used all the time. The bottom of your car is painted with a zinc coating. Sometimes you can buy, let's look up, this nail here. You notice anything interesting about it? It's kind of got a matte finish, doesn't it? It's not shiny like that nail. Matte finish.
It looks almost like it's slightly been kind of like sanded away, like it's not exactly.
Does anybody know what's happened here?
It's been galvanized.
What does that mean? What does galvanized mean as far as hardware goes?
Rust resistant?
It applies to what we just talked about with the Statue of Liberty.
It's a rust proof.
What's the coating on it? It's not rust proof. It's zinc.
Okay.
So they take zinc and they turn it into like a paste. So they have this paste of zinc metal, actual elemental zinc, and then they coat the nails with it. So what's going to happen to this nail over the course of 5-10 years? The zinc is going to corrode. But what's not going to corrode?
The actual nail metal, like the iron.
The iron underneath isn't going to corrode. So if you like put a fence together with galvanized nails, you'll see like some staining underneath the nail as the zinc turns into a salt and then dribbles down and dries out the wood underneath it. So this will make those nails last many years longer. So you would use these for outdoor purposes. There's no need to have them on the inside. If your house is, you're putting together studs that are going to be protected by a roof, then you don't have to worry about it. They also make the galvanized metal roofs, right? So like those tin roofs, aluminum roofs, they galvanize the surface of that so the metal actually underneath doesn't rust. It's a way to get around painting, or a way to make it so that the metal still looks like metal instead of just being painted. All right, what else with this? When's the exam?
Next week, next Thursday.
Is it next Thursday?
Mm-hmm.
Okay. Alrighty. Well, that does it for the day. We'll talk about the last few pages of this on Tuesday, and then be ready for the exam on Thursday.
Okay.
I'll see you guys later.
Goodbye. Have a good day.
Have a good weekend. Yep.
Will it be the same as it was last time? We have it on Wednesday.
I'm sorry, say that again.
Will the homework be the same way it was last exam, where we'll have one due Wednesday?
Yeah, I'll probably do that. Just so you can get more practice problems in.
Bye, Rob. Thank you.
See you guys later.